Hello there, and welcome to Fall Asleep. Tonight, we are going somewhere that no human has ever truly visited. Not a forest at the edge of winter, not an ocean floor where the water is black and cold and perfectly still. Not even the surface of another planet, with its alien dust and unfamiliar sky. Tonight, we are going somewhere far stranger than any of those places. We are going to the edge of time itself. Not time as we experience it in the small, daily sense. Not the time that passes while you wait for a kettle to boil, or the time that seemed to stretch endlessly on a childhood afternoon. We are going to time as a physical thing, a dimension of the universe, a thread woven into the fabric of space that can be pulled, compressed, and stretched by the presence of mass. We are going to a place where the universe does something quietly extraordinary, where gravity does not just pull things downward, as you feel it now pressing you gently into the surface beneath you, but actually slows the passage of time, where a clock ticking on one hillside runs ever so slightly slower than a clock ticking on the hilltop above it, where, near the crushing heart of a massive star, time itself becomes something that bends and stretches and softens into something almost unrecognizable. This is not a story from science fiction. It is not a thought experiment invented by a philosopher to make students uneasy. It is real. It has been measured. It has been proven in laboratories with atomic clocks flown on airplanes. In satellites that orbit above us right now, their clocks carefully adjusted each day, because time genuinely passes at a different rate up there. And in the elegant mathematics of a mind that changed everything we thought we knew about the nature of reality. This is the story of time dilation near a massive star, and it begins, as so many great stories do, with one person who refused to accept that the universe was simple. Before we drift into the cosmos together, if you find these quiet journeys restful, I invite you to like, subscribe, or leave a gentle thought below. It helps other tired minds find their way here too. One sleepy soul at a time. But for now, there is nothing you need to do. Nothing you need to plan. Nothing you need to remember. All you need to do is let your shoulders drop. Let your jaw unclench. Let your hands open and soften where they rest. Let your breathing become slow and easy and natural, like the breathing of someone who has already let the day go. And as your mind begins to gently release the weight of everything it has been holding, join me as we travel outward, past the edge of everything familiar, into the soft, slow pull of space-time itself. Let us begin. To understand time dilation, we first need to understand that time is not what we think it is. This is not a small idea. It is an idea that tends to shift slightly every time you return to it. Growing stranger. The way a room you remember from childhood changes when you revisit it as an adult, except in reverse. The room does not get smaller when you understand it better. It gets larger, more complex, more worthy of wonder. For most of human history, time was considered absolute, fixed, universal. It ticked forward at the same steady rate for everyone, everywhere, without exception. Whether you stood on a mountaintop in the cold, clear air, or sat in a deep valley where the light came late and left early, whether you sat perfectly still in a quiet room, or moved at great speed across a landscape, whether you were far from any star, drifting through the emptiness between galaxies, or close to one, feeling its radiation on the hull of your spacecraft, time was time. 1 second here was 1 second there. They were always the same. That was the assumption woven so deeply into the foundations of physics that few people questioned it at all. It felt as obvious as the fact that the ground is solid. Isaac Newton, one of the greatest minds science has ever produced, built his entire framework of mechanics on this assumption, and his framework worked astonishingly well. For more than 200 years, Newtonian mechanics described the motion of planets with extraordinary precision. It traced the arc of cannonballs. It explained the pull of the moon on the tides. It allowed engineers to build bridges and astronomers to predict the position of planets decades into the future. It was elegant. It was powerful. It felt complete. It felt like an ending, like the place where physics had finally arrived at its permanent home. Then, at the very end of the 19th century, something began to crack. Quietly at first, just a hairline fracture in the foundation. The kind that is easy to ignore for a while. Physicists started noticing that the speed of light behaved in a deeply peculiar way. Most scientists at the time assumed that light traveled through a medium called the ether, a kind of invisible substance that filled all of space. If that were true, the speed of light should vary depending on your motion through that medium, the same way the speed of sound changes depending on the wind. Experiments were designed to measure this effect. The most famous was performed by Albert Michelson and Edward Morley in 1887. They built a precise instrument to compare the speed of light traveling in different directions. They found no difference. No matter how the apparatus was oriented, no matter what direction Earth was moving, the speed of light was always the same. And this was not a little strange. It was profoundly, unsettlingly strange. If you run toward an oncoming train, the train reaches you faster. This is obvious. But light did not behave like a train. Light always traveled at roughly 300,000 kilometers per second, regardless of how the observer was moving. This single result was a splinter under the fingernail of classical physics. And one young person, working quietly in a patent office in Switzerland, would eventually remove it by rewriting the rules of reality. Albert Einstein was 26 years old in 1905. He had earned a degree in physics but had been unable to find a position at a university. He worked instead as a technical expert at the Swiss Patent Office in Bern, reviewing applications, making modest recommendations, earning a reliable salary. He had no laboratory. He had no team of graduate researchers to run experiments and gather data. He had no prestigious institution behind his name, no famous supervisor vouching for the quality of his ideas. He had a small desk, a modest salary, and an extraordinary mind that would not stop asking uncomfortable questions. Questions like, what would it look like to ride alongside a beam of light? What would happen to time if you move fast enough? What does it actually mean to say that two events happen at the same moment? These were not casual questions. They were questions that had quietly destabilized his thinking for years. And in that single year, 1905, which physicists now call his annus mirabilis, his miraculous year, he published 4 papers that transformed physics more completely than anything since Newton. One introduced the concept of the photon, a particle of light, which would later earn him the Nobel Prize. And one introduced the special theory of relativity. It began with 2 deceptively simple postulates. The first, the laws of physics are the same for all observers moving at constant velocity, whether you are standing still in a laboratory or drifting through space at 10,000 kilometers per hour. The same physical laws apply. The second, the speed of light in a vacuum is always the same for all observers, regardless of how they move or how the source of light is moving. Always 300,000 kilometers per second. Always. From these 2 ideas, consequences followed that seemed completely impossible if you had spent your entire life inside Newton's framework. Space and time were not separate things. They were woven together into a single entity called spacetime, and the measurements of space and time that an observer made depended on their motion. Time passes differently for objects moving at different speeds. A clock on a fast-moving spaceship ticks more slowly than a clock sitting still on Earth. Not because the clock has been damaged, not because of any mechanical difference, but because time itself, for that moving observer, actually passes at a genuinely different rate. This was called time dilation, And while it sounds like fantasy, it is physics. Pure, testable, rigorously verified physics. The faster something moves relative to an observer, the slower time passes for it from that observer's perspective. At speeds we encounter in everyday life, the effect is far too small to notice. But as you approach the speed of light, it becomes dramatic. A traveler moving at 99% of the speed of light would age far more slowly than the people they left behind. For every second that passed for them, roughly 7 seconds would pass for a stationary observer. Time, it turns out, is not a universal river flowing at the same rate for everyone. It is more like a fabric, a flexible, stretchable fabric, and that fabric can be stretched by motion, and, as Einstein would show a decade later, by something else entirely. By gravity. Special relativity was only the beginning. It described what happened to space and time for observers moving at constant velocity. But it said nothing about acceleration, nothing about gravity. And gravity is everywhere. It is the force that shaped the universe from its earliest moments. It gathered clouds of gas into the first stars. It pulled those stars together into galaxies. It keeps planets in their orbits, moons circling planets, and all of us pressed gently against the ground as we sleep. Einstein spent the next decade working on the problem of gravity. It was harder than special relativity. Far harder. He described it later as the greatest intellectual struggle of his life. He had moments of thinking he had found the answer, only to discover an error in his mathematics. He began again. He refined. He rethought. He arrived at ideas that felt almost too strange to be true, and then stayed with them long enough to realize they were exactly right. In November of 1915, he presented his final equations to the Prussian Academy of Sciences in Berlin, the general theory of relativity. The central insight was startling in its elegance. Gravity is not a force pulling things together across empty space. There is no invisible thread connecting the Earth to the Sun, no pull being transmitted instantaneously across millions of kilometers. Gravity is the curvature of space-time itself. Massive objects, stars, planets, black holes, do not emit a gravitational force. They bend the fabric of space-time around them, and other objects, free to follow the natural paths available to them in that curved space-time, appear to be attracted to the massive object. They are not being pulled. They are following the curves in the fabric. The way a marble rolling across a stretched rubber sheet curves toward a heavy ball, placed in the center, not because it is attracted to the ball, but because the surface beneath it is no longer flat. And this picture of gravity brought with it a consequence that Newton never imagined. Just as special relativity showed that motion affects the passage of time, general relativity showed that gravity does too. The stronger the gravitational field, the more slowly time passes. This is called gravitational time dilation. Sit at the base of a tall mountain, where gravity is marginally stronger, and your clock ticks ever so fractionally slower than a clock at the summit. The difference at that scale is almost impossibly small, but it is real. It has been measured by physicists who flew atomic clocks on aircraft at high altitude and compared them carefully to clocks that stayed on the ground. The clocks that flew higher ran fractionally faster, just as general relativity predicted. And near truly massive objects, stars many times larger than our sun, the effect becomes not fractional, but profound. Time near a massive star runs slower than time far away from it. Not just a little slower. Measurably, significantly, undeniably slower. The universe is not neutral about where you are. Your position in a gravitational field determines the rate at which your moments unfold. Let that settle for a moment. Time itself depends on where you stand. Not your perception of time. Not your psychological experience of it. Time itself, the physical quantity, the dimension of the universe in which all change occurs. It passes at different rates in different places, and that difference is shaped by mass. To feel the weight of this idea, imagine two clocks, identical in every way, made by the same manufacturer, from the same materials, tested and verified to run at precisely the same rate. They were placed side by side and synchronized perfectly before the experiment began. Their readings matched to within a fraction of a nanosecond. Now they are separated. One clock is placed aboard a small probe and sent far out into deep space, away from any significant source of gravity. It floats there in the quiet dark, ticking faithfully, undisturbed. The other clock is lowered carefully toward the surface of a massive neutron star. These stars are among the most extraordinary objects in the known universe. They are the collapsed remnants of stars that once burned far brighter and hotter than our sun. Stars perhaps 8 to 20 times the mass of our sun, that burned through their fuel in a matter of millions of years, and then ended in a catastrophic explosion. When those explosions occurred, the outer layers of the star were blasted into space, leaving behind the core. And the core, no longer supported by the energy of nuclear fusion, collapsed inward under its own gravity. The collapse was not gentle. Protons and electrons were crushed together into neutrons. The entire core compressed in less than a second into a sphere roughly 20 kilometers across. 20 kilometers. The distance you might drive to reach the nearest large city, containing more mass than the sun itself. The gravity at the surface of a neutron star is roughly 200 billion times the surface gravity of Earth. On Earth, gravity accelerates you downward at about 10 meters per second. On a neutron star, that same acceleration is 2 trillion meters per second. A person of 70 kilograms would weigh approximately 7 trillion kilograms at that surface. This is not merely very strong gravity. It is gravity of a different order entirely. And our clock rests there, at that surface, ticking faithfully in conditions we can barely imagine. Back out in deep space, the distant clock ticks too. Both clocks are working perfectly, but they are not ticking at the same rate. The clock near the neutron star is ticking more slowly. Not because anything is wrong with it. Not because the gravity is interfering with its mechanism, but because time itself is genuinely passing more slowly at that location. The fabric of spacetime is more deeply curved near that massive object, and in more deeply curved spacetime, time passes more slowly. If you could observe both clocks from a safe distance, you would see them falling out of sync, second by second, hour by hour, day by day. After 1 year measured by the distant clock, the surface clock would show something less than a year, perhaps 60 to 70% of the year the distant clock measured. Near enough to a sufficiently massive object, the difference becomes not seconds or minutes, but hours, days, months, years. The universe has been quietly arranging this around every massive object in existence since the very first stars began to burn, billions of years ago, long before anything was alive to notice. Our planet is not a neutron star. Its gravity, while real and constant and felt in every moment of our lives, is gentle by comparison to what we have just imagined. We are fortunate to live on an object whose gravity is gentle enough for life to emerge, for oceans to exist in liquid form, for mountains to stand and trees to grow and not be crushed flat by their own weight. And yet, the gravity of Earth is real enough for time dilation to be measurable. Clocks at sea level, where gravity is slightly stronger due to proximity to the center of the Earth, tick fractionally more slowly than clocks on a high mountaintop. The difference is extraordinarily small, a few microseconds per year, nothing any human could ever feel in the ordinary course of living. You do not notice yourself aging marginally faster at the beach than at altitude. Your body has no way to detect differences of microseconds in a year. but our technology does. And it matters enormously. The global positioning system, the network of satellites that allows the device in your pocket to tell you exactly where you are on the surface of this planet, depends on timing so precise that relativistic effects cannot be ignored. The system works by measuring the time it takes for signals to travel from multiple satellites to your device. By comparing the arrival times of signals from several satellites, your device can calculate its position with remarkable accuracy. The satellites orbit Earth at roughly 20,000 kilometers altitude. Up there, two competing relativistic effects are at work simultaneously. First, the satellites are moving at roughly 14,000 kilometers per hour relative to the ground. This velocity causes their clocks to tick slightly more slowly due to velocity-based time dilation from special relativity. Moving clocks run slow. At that orbital speed, this effect causes the satellite clocks to lose about 7 microseconds per day relative to ground clocks. Second, the satellites are farther from Earth's center, where the gravitational field is weaker. In weaker gravity, time passes slightly faster. This gravitational time dilation from general relativity causes the satellite clocks to gain about 45 microseconds per day relative to ground clocks. These two effects act in opposite directions. The velocity slows the clocks slightly. The weaker gravity speeds them up slightly. The net result is that satellite clocks gain roughly 38 microseconds per day relative to clocks on the ground. 38 microseconds. A unit of time so small it is almost impossible to visualize. And yet, GPS navigation depends on nanosecond level precision. 1 microsecond of timing error translates to roughly 300 meters of positional error. 38 microseconds per day would produce errors of about 11 kilometers per day. Within hours of operating without relativistic corrections, your navigation would be useless. But the corrections are applied. Every satellite in the GPS constellation has its clock adjusted to account for both forms of time dilation. Every time you navigate by satellite, you are being guided by a technology that only functions because Einstein was right about something that sounds like science fiction. Relativity is not abstract. It is embedded in everyday life in ways most of us never stop to consider. Now let us move further. Let us leave the familiar gravity of Earth and travel outward, toward objects where gravity is far more powerful. In our galaxy alone, there are estimated to be roughly 200 to 400 billion stars. Most of them are smaller than our Sun, red dwarfs, dim and cool, burning their fuel with great patience over timescales that stretch into the trillions of years. But a fraction of those stars are far more massive. Imagine a star about 10 times the mass of our Sun. Such stars are called B-type or O-type stars, depending on their exact temperature and mass. They burn hotter and bluer than our yellow Sun. Their surface temperatures can reach 20 to 50,000 degrees Celsius, compared to the roughly 6,000 degrees of the Sun's surface. They shine with a brilliance that makes our own Sun look modest by comparison. A single star of this type might radiate as much energy as 10,000 suns. Their light, if you could see it from a habitable distance, would be an intense blue-white, not the warm golden yellow of a summer afternoon. Something colder, fiercer, more austere. The gravitational field at the surface of such a star is vastly stronger than anything we experience on Earth. Not hundreds of times stronger, not thousands, but tens of thousands of times stronger. At the photosphere, the visible surface of such a star, time runs measurably more slowly than it does in empty space nearby. The difference is not as dramatic as near a neutron star, but it is real, and it is not just the surface of the star that is affected. The entire gravitational field extending outward from the star causes space-time to curve. Any clock placed within that field, even at a significant distance, ticks slightly more slowly than a clock far outside it. The effect diminishes with distance, falling off according to precise mathematics, but it never reaches zero until you are infinitely far away. Every massive star in the galaxy is quietly warping the time and the space around it. Every one of the hundreds of billions of stars in our galaxy alone, each one bending space-time according to its mass, each one causing time to pass at a slightly different rate in its vicinity. The universe is saturated with gravitational fields. There is no location in the cosmos that is perfectly flat space-time, perfectly free of all gravitational influence. There is always something massive somewhere, always a star, always a galaxy, always a cluster of galaxies exerting its subtle pull on the fabric of space and time. We live immersed in a universe where the flatness of space-time is an ideal that is never quite achieved. And this means time dilation is not an exotic phenomenon that occurs only in laboratories or near extreme objects. It is happening everywhere, all the time. Right now, in the space between words, in the pause between breaths, in every quiet moment of every ordinary life. When massive stars reach the end of their lives, something happens that pushes time dilation to its most extreme expression. They die. And they die spectacularly. The life of a massive star is a story of balance. For millions of years, the star maintains an uneasy equilibrium between two opposing forces. The first is gravity. The star is so massive that its own gravity is constantly trying to collapse it, trying to crush it inward, trying to compress it into something smaller and denser. The second force is pressure. At the core of the star, nuclear fusion converts hydrogen into helium, releasing enormous amounts of energy. That energy pours outward, creating pressure that pushes back against gravity. For millions of years, these two forces balance. The star neither collapses nor explodes. It simply burns. Steadily, magnificently, in the dark of space. But the hydrogen does not last forever. When the core runs out of hydrogen, the balance breaks. Gravity begins to win. The core contracts. As it contracts, it heats up. Eventually, it grows hot enough to ignite the next fuel. Helium. Helium fuses into carbon and oxygen. The star burns again. But this stage does not last as long. When the helium runs out, the core contracts again. Temperatures rise again. Carbon ignites, then neon, then oxygen, then silicon. Each stage burns faster than the last. The hydrogen burning took millions of years. The helium burning, hundreds of thousands. The carbon burning, a few thousand years. The oxygen burning, a few months. The silicon burning, a few days. At the end of silicon burning, the core fills with iron. Iron is the end of the road for stellar fusion. Elements lighter than iron release energy when they fuse. Elements heavier than iron require energy to fuse. Iron cannot yield energy through fusion. It simply accumulates in the core, growing denser, growing more massive, pressing down with increasing weight. When the iron core grows to roughly 1.5 times the mass of our Sun, something catastrophic happens. In a fraction of a second, less time than it takes to blink, the core collapses. Protons and electrons are forced together, forming neutrons and ghostly particles called neutrinos. The core shrinks from roughly the size of Earth to roughly the size of a city in less than a second. The outer layers of the star, which had been falling inward, strike the now rigid neutron core and rebound. A shockwave of unimaginable force tears outward through the star. The supernova, an explosion so powerful that it briefly outshines the entire galaxy in which it occurs. And left behind at the center, quiet and impossibly dense, is either a neutron star, or, if the collapsing core was massive enough, something even more extreme, a black hole. where time dilation reaches its most dramatic expression anywhere in the known universe. A supernova, at its peak, can radiate more energy in a single second than the sun will produce in its entire 10 billion year lifetime. The shockwave travels outward at roughly 10% of the speed of light, carrying with it the heavy elements forged in the star's core: iron, nickel, silicon, calcium, all of it scattered into space, available to be swept up by passing gas clouds, incorporated into new stars, into planets, into whatever might eventually live there. This is how the atoms of life travel between stars. Not carried, not sent, simply scattered. And in the silence that follows, the neutron star or black hole at the center quietly bends the spacetime around it, slowing time, doing what all massive objects do in the patient language of general relativity. The boundary around a black hole, the invisible threshold beyond which nothing returns, is called the event horizon. It is not a physical surface. There is no wall, no barrier you could see or touch. Nothing visible would mark the boundary. If you were falling toward a black hole and you crossed the event horizon, you would not feel any particular boundary. No wall of fire, no sudden jolt, no alarm telling you that you had passed the point of no return. You would simply be inside. The event horizon is defined by the mathematics of gravity. It is the location in space where the escape velocity equals the speed of light. Escape velocity is the speed you need to break free of a gravitational field. On Earth, it is about 11 kilometers per second. Fast, but achievable. Near a black hole, as you approach the event horizon, the escape velocity rises. At the event horizon itself, it equals the speed of light, 300,000 kilometers per second. Nothing can travel faster than light. Therefore, nothing can escape. Not light, not information, not anything. Whatever passes inside, stays inside. For an outside observer, watching someone fall toward a black hole, the experience is one of the strangest that the physics of our universe allows. As the falling person moves deeper into the gravitational well, the light they emit must work harder and harder to climb back out against gravity. Light is affected by gravity. Einstein predicted this too. Light traveling out of a gravitational field loses energy as it climbs. It is redshifted. Its frequency decreases. Its wavelength stretches. And this stretching has a time-related interpretation. The frequency of light is essentially a clock. When that frequency decreases, when the light is redshifted, it means the oscillations are arriving more slowly. This is gravitational time dilation expressed in light itself. For the outside observer, watching someone fall toward a black hole, the falling person appears to slow down. Their movements stretch. Their waving hand takes longer to complete its arc. Their voice, if it could somehow be received, would be drawn out, slowed. They appear to slow and slow and slow. As they approach the event horizon, they seem to almost stop. Frozen in time. Suspended at the edge of the unreachable. Eventually, they fade entirely from view. The last photons of light, struggling to climb out of that gravity, arrive with wavelengths so long they carry no visible signal. From the outside, the person has been erased by time dilation, frozen at the edge of eternity. And yet, from the perspective of the falling person, nothing unusual has happened. They feel no jolt. They notice no slowing. They cross the event horizon without any particular sensation marking the moment. Time, for them, passes normally. It is only relative to the outside observer that their time has stretched and finally become, from the outside perspective, almost infinitely slow. Gravitational time dilation reaches its most dramatic expression here, at the edge of a black hole. There is a thought experiment that physicists have used for decades to make the strangeness of time dilation more vivid, more personal, more felt. Imagine two siblings, born on the same day, who have always been the same age. Let us call them Mara and Ren. Mara is restless. She has always wanted to go further than anyone has gone, to see what lies beyond the comfortable, familiar sky. Ren is quieter, happy to stay, happy to wait, happy to watch the stars from the surface of their home world. And imagine where Mara has gone. One day, Mara boards a spacecraft equipped with technology far beyond anything we currently possess. Her ship can approach the surface of a massive neutron star without being destroyed, shielded from the radiation, stabilized against tidal forces, hovering in place by powerful engines that work against the pull of gravity. She descends toward the surface of the neutron star and holds her position there. From her perspective, nothing unusual happens. Time passes normally. Her clocks tick at their regular rate. She eats, sleeps, reads, thinks. She watches the strange compressed sky above her, the stars distorted by the curved spacetime around the neutron star. She spends what feels to her like 1 year, 365 days, measured by her own heartbeat, her own hunger, her own sleeping and waking. Meanwhile, far out in space, Ren waits. Ren's clocks tick. Ren's days pass. Ren ages. After 1 year of Mara's time at the surface, she fires her engines and climbs back out of the gravity well, back to where Ren is waiting. When they embrace, they are no longer the same age. Ren is older, because time at the neutron star passed more slowly for Mara. The universe continued at its normal pace for everything outside that gravity well. 1 year for Mara was something more than 1 year for Ren, depending on the mass of the neutron star and how close Mara hovered. The difference might be months, or years, or, near a sufficiently extreme object, even decades. This is not a paradox. It is not a contradiction. It does not violate any principle of physics. It is a direct prediction of general relativity, a theory that has been tested with extraordinary precision and found to be correct at every turn. The twin who spent time in the stronger gravitational field aged less. Not subjectively, not because of any trick of perception, but because the physical process of aging, which is ultimately a series of chemical and biological events unfolding in time, ran at a slower rate in the curved spacetime near the neutron star. Every heartbeat took a little longer. Every cell division took a little longer. Every thought took a little longer. Not because the biology was different, because time was different. The universe does not play favorites. It simply obeys its own mathematics. And its mathematics says that time is not the same everywhere. It never was. Let us think about what this means on a cosmic scale. The universe is approximately 13.8 billion years old. In that time, generations of stars have been born, have burned, and have died. The first stars formed a few 100 million years after the Big Bang, when the diffuse gas of hydrogen and helium that filled the young universe began to collapse under gravity into the first stellar objects. Those first stars were likely enormous, far more massive than most stars that exist today. Some may have been hundreds of times the mass of our sun. They burned intensely and briefly, consuming their fuel in only a few million years. When they died, their deaths seeded the universe with heavier elements: carbon, oxygen, nitrogen, iron, gold. Elements that did not exist before the first stars processed their lighter fuel. Elements that would eventually be incorporated into later generations of stars, into planets, into oceans, into living things. You are made in part of atoms that were forged in the cores of stars that died billions of years ago. The iron in your blood, the calcium in your bones, the oxygen filling your lungs right now, slowly, as you breathe. All of it was made inside stars. All of it passed through the gravitational heart of objects, where time moved at a different rate than it does here. And around those ancient stars, as they burned in the young universe, time was being curved. Space-time was bending around each massive object. Clocks near them would have run slower than clocks far away. This was true billions of years before any beings existed to make clocks. It was true billions of years before any beings existed to think about time at all. The universe did not wait for us to discover time dilation before implementing it. It has been running this way since the very first mass condensed from the primordial gas. And it will continue long after the last star has burned out and the universe has grown dark and cold. The mathematics does not require observers. It does not require understanding. It simply requires mass and space-time and the relationship between them that Einstein described in the autumn of 1915, long before we named it, long before we measured it. The universe was bending time around every bright point of light in the sky above you. It still is. Right now, consider what that means for the history of life on Earth. For 4 billion years, living things have been evolving on this planet. Every heartbeat of every creature that ever lived here, every moment of every life, unfolded at the rate that Earth's gravitational field allowed, slightly slower than it would have unfolded in empty space. The difference is vanishingly small, but it was always there. And those ancient massive stars whose explosions seeded our solar system with the elements that make us up, those stars lived their lives in their own gravitational fields, far stronger than Earth's. The processes that built the heavy elements inside them, the fusion that produced the carbon and iron now in your body, all of it happened in a space-time more deeply curved than the one we inhabit. The atoms in your body were forged in a different flow of time than the one you are experiencing right now. Before you were born, before Earth existed, before our sun ignited, the matter that makes you pass through hearts of stars where time ran differently, it arrived here, in this gentler gravity, and eventually became the molecules of a living person, breathing slowly in a quiet room, at rest. There is something quietly beautiful about what general relativity tells us about pulsars. These are a specific type of neutron star, and they are among the most remarkable objects our observations have revealed. When a neutron star forms from the collapsed core of a dying massive star, it inherits the rotation of its parent. The original star rotated, as all stars do, slowly, over the course of days or weeks. When the core collapses to a sphere 20 kilometers across, conservation of angular momentum, the same principle that causes a figure skater to spin faster when they pull in their arms, causes the rotation to accelerate dramatically. Some neutron stars rotate many times per second. Some rotate hundreds of times per second. The fastest known pulsar rotates over 700 times per second. 700 complete rotations in a single second. At the equator of such a star, the surface is moving at a significant fraction of the speed of light. These rapidly rotating neutron stars emit beams of electromagnetic radiation from their magnetic poles. The magnetic poles do not necessarily align with the rotational poles. So as the star rotates, the beams sweep through space like the light from a lighthouse. If Earth lies in the path of one of these beams, we detect a pulse of radio waves with each rotation. Regular, precise, rhythmic, like a heartbeat from the distant dead. The pulses from some pulsars arrive with such extraordinary regularity that they rival the best atomic clocks we have ever built. Some pulsars are accurate to better than 1 part in 100 trillion. We use the best pulsars as standards of measurement for detecting ripples in space-time from colliding black holes billions of light years away. But here is where time dilation quietly enters the story. Some neutron stars exist in binary systems, paired with another neutron star, or with a white dwarf. They orbit each other, moving through the gravitational field of their companion, accelerating and decelerating as they swing through their orbits. And all of these motions affect the timing of the pulses we receive. When the emitting pulsar is closest to its companion, deepest in the companion's gravity well, time runs slightly slower for it. The pulses arrive slightly less frequently than expected. When it moves to the far side of its orbit, farther from the companion's gravity, time runs slightly faster. The first binary pulsar system was discovered in 1974 by Russell Hulse and Joseph Taylor. They tracked its pulses with extraordinary care over many years, and they found that every prediction of general relativity was confirmed. The orbital decay, the gravitational redshift, the time dilation, all of it, exactly as Einstein's equations predicted. Hulse and Taylor received the Nobel Prize in Physics in 1993 for this discovery. The universe is patient. It does not announce its rules loudly. It writes them in the timing of distant pulses, in the drift of microseconds, in the quiet rhythm of stars that died long ago. You are lying very still now. The day has receded. The thoughts that pressed close earlier, the tasks, the small worries that felt large, have begun to loosen their hold. Your breathing has found its own pace, slow, easy, unhurried. The room around you is quiet, and somewhere above you, above the ceiling, above the roof, above the thin shell of air that clings to this small planet, satellites are orbiting. Right now, as you lie here, their clocks are ticking at a slightly different rate than yours. The difference is real. It has been measured. It has been accounted for in the design of the systems that guide ships, aircraft, and the small illuminated screen you carry in your pocket. Now let your imagination drift outward, past the satellites, past the moon, which floats in the dark 250,000 miles away, its gravity tugging gently on the water of the oceans, raising tides, a slow, faithful rhythm. Past Mars, the small red world, its thin atmosphere offering little protection against the sun's radiation, its surface cold and ancient and still. Past Jupiter, enormous and banded, its gravity so strong that it acts as a shield for the inner planets, catching wayward comets before they can reach us. Past Saturn and its rings, those thin sheets of ice and rock that circle the planet in an arrangement so perfect it still seems, after all the images we have gathered, a little impossible. Past the outer planets, past the heliopause, where the solar wind meets the thin gas of interstellar space, the edge of the sun's domain, and then outward into the vast stillness between stars. Space here is not empty in any emotional sense. It is full of something, a deep, patient quiet. The kind of quiet that is not the absence of sound, but the presence of something ancient and expansive that has never needed noise. And then onward, toward one of the bright points of light you may have watched from a window as a child. As a child, the stars were simply beautiful. Distant sparks, mysterious, familiar in their constancy. Now you know that each one of those points of light is a place, a massive object burning in the dark, bending space-time around itself, slowing time in the space it occupies. Each star you approach begins to assert its gravity. Space-time curves around it. As you draw closer, the seconds begin to stretch. Time begins to soften. You would not feel it. There is no sensation of slowing, no heaviness in the chest. You would simply be there, living your moments at the rate they arrived, while outside the curve of that star's gravity, the universe was ticking at a slightly different pace. This is one of the most remarkable properties of time dilation. It is invisible from the inside. You cannot feel it happening. It is only apparent in comparison. The universe keeps its accounts quietly, with perfect precision, without error. Let us imagine something more specific. You are in a spacecraft, Perhaps it is something soft and quiet, more like an observation room than a vehicle, with large curved windows and gentle light and deep chairs. You are approaching a massive blue star, not dangerously close, but into an orbit that brings you near enough for the star to fill a quarter of your sky. You have time to look. You have time to simply be there and observe. The star burns blue-white with an intensity that the windows automatically dim to protect you, even filtered. The light has a quality unlike anything you have experienced before. It is not the warm golden light of a summer morning. It is something fiercer, cleaner, more austere. The surface of the star is not still. Massive convection cells circulate beneath the photosphere. Enormous magnetic flux tubes rise from below, creating structures on the surface that are darker than the surrounding plasma, but still thousands of degrees hot. Filaments of superheated gas arch outward in graceful loops along magnetic field lines, stretching for thousands of kilometers, then falling back. The star is alive with motion, and time, for you, continues to pass. One breath, then another. A heartbeat, a thought, a shifting of your gaze from one part of the star to another. Nothing feels unusual. Nothing feels slow. But if you had brought with you a perfect communication link to Earth, a careful comparison of timestamps would reveal that your clock and their clock were no longer synchronized. Your minutes are fractionally longer. Your seconds have stretched by a tiny, precise amount, calculated exactly by the Schwarzschild metric, one of the first exact solutions to Einstein's field equations. It was derived by the German astronomer Karl Schwarzschild in 1916, while he was serving on the Russian front in the First World War. He solved these equations from the trenches. He found an exact mathematical description of the spacetime around a spherical mass. He died months later, before he could know how important his solution would become. But the equations survived him, and they correctly describe the time dilation you are experiencing now, in this imagined orbit, around this imagined star. The universe has a mathematics. It does not require anyone to believe in it for it to be true. It does not require anyone to understand it. It simply is, and you are embedded in it, in this moment, orbiting quietly in the stretched seconds of a gravitational well. Breathing softly, watching the light. Letting time do what it has always done in places like this, long before anyone was here to watch it. The star does not know you are here. It has no awareness of your presence, no response to your watching. It burns because the physics of its core demands that it burn. It will continue long after your visit ends, long after any record of your visit has faded. And somewhere in the faint difference between your clock and Earth's, the universe is quietly keeping its accounts, writing the divergence. Perfect, impersonal, patient. There is a version of time dilation that happens close to the ultimate extreme, not near a neutron star, not near a massive blue star, near a black hole, and not just any black hole. At the centers of most large galaxies, including our own Milky Way, there exist objects called supermassive black holes. They range in mass from millions to billions of times the mass of the Sun. At the center of our galaxy, roughly 26,000 light-years away, there is a supermassive black hole called Sagittarius A star. Its mass is approximately 4 million times the mass of the Sun. In 2022, the Event Horizon Telescope collaboration released the first image of the shadow of this object. A blurry ring of light, photographed by a network of radio telescopes spanning the entire Earth, working together as a single instrument, a photograph of the boundary of darkness. The first direct visual evidence of the object that sits at the heart of our galaxy. The event horizon of Sagittarius A star is approximately 24 million kilometers across, roughly half the distance from the Sun to Mercury. Near an object of this mass, gravitational time dilation is extreme. A rotating black hole does not merely curve spacetime. It drags spacetime into rotation with it. This effect, predicted by general relativity and confirmed by observations, is called frame dragging, or, more formally, the lens-thirring effect. Even light, trying to travel in what would be a straight line in flat spacetime, finds its path twisted by the rotation of spacetime itself. This was confirmed by NASA's Gravity Probe B mission, which launched in 2004 and measured frame dragging around the Earth. The Earth is not a black hole, but it is massive enough that its frame dragging effect was measurable with instruments of sufficient precision. Near a supermassive black hole, the effect is vastly stronger. An observer hovering just outside the event horizon would experience time passing at a rate so slow relative to the outside universe that comparisons become almost meaningless. While they experienced 1 year, the distant universe might age by millions of years. Stars might form and die in the outer arms of the galaxy. Civilizations might emerge, flourish, and vanish. Entire geological epochs might pass on distant worlds. The observer would emerge, if they could, into a universe older than their own past by an almost incomprehensible margin. This is not exaggeration. This is what general relativity predicts, confirmed by numerous tests and observations over more than a century. Gravitational time dilation. Real, precise, extreme near extreme mass. Present everywhere there is gravity. Present here. Present here. Present now. Present in the gentle pull of the world beneath you as you rest. An atomic clock placed at the base of a building runs slower than one on the top floor. Not because something is wrong with it, but because the physics of atomic transitions, the quantum processes inside the atoms, run at the rate that time dictates at that location. The clock is not measuring time dilation. The clock is living it. Every atom in your body is living it too. Every slow rhythm of your breathing as you lie here now is unfolding at the rate that Earth's gravitational field allows. You are not observing space-time from outside. You are the clock, softly ticking, at rest. As we come gently to the end of our journey tonight, let the ideas we have visited drift softly like starlight crossing the patient dark between galaxies. We began with a universe that seemed fixed, stable, comprehensible in the way of clocks and rulers and steady, universal time. And we discovered that this was never true. Not for a single moment in the history of the universe was this true. Time is woven into space itself, into a fabric called spacetime, that bends and curves wherever mass is present, and mass is present everywhere. We followed a young man working at a patent desk in Switzerland, asking quiet questions that no one else was asking, and arriving at answers that rewrote everything. We saw how the equations he wrote live today in the satellites above us, in the navigation systems we use without a second thought, in the clocks that must be corrected daily, because time genuinely passes at different rates at different altitudes. We visited the dense, quiet remnants of stars, neutron stars rotating hundreds of times per second, sending pulses across the galaxy like slow, faithful heartbeats from the long dead. We watched binary pulsars confirming Einstein's predictions with extraordinary precision, the timing of their pulses encoding the gravitational time dilation of their orbits. We stood at the edge of black holes and imagined watching the universe age at breathtaking speed while our own moments stretched and deepened and slowed. And through all of it, one idea stayed close. You were never outside this story. You are in it. Right now, at the altitude of your bed, in the gravitational field of this planet, your clocks are ticking at a rate ever so slightly different from clocks on a mountaintop or on a satellite overhead. You are embedded in space-time. You are part of the fabric, the same gravity that curved the paths of ancient stars, The same mathematics that Schwarzschild worked out in a trench over 100 years ago applies to you, here, now, in the warmth of this quiet room. You are not separate from the cosmos. You are woven into it, made of atoms forged in stars, breathing air shaped by billions of years of planetary evolution. Living your moments at the pace that the local curvature of space-time allows. There is nothing more you need to hold tonight. Let the equations dissolve. Let the massive stars cool and quiet themselves in the dark behind your eyes. Let the neutron stars settle back into the silence from which they came. Let the black holes close their edges into stillness. Let the pulsars tick on without you, patient and faithful, in the far dark. And let yourself sink into the slow, unhurried passage of your own moments. Time is soft tonight. The universe is vast and old and does not require anything from you right now. It was old before you arrived. It will continue long after any of us can imagine. And in this small corner of it, in this quiet room, in the gentle gravity of this small planet, you are exactly where you are meant to be. Resting. Still. Safe. If you are still with us, another quiet journey is waiting for you. And if this one helped carry you towards sleep, a like, a subscribe, or a gentle comment helps other tired minds find their way here too. From fall asleep, and from one tired mind to another, across the soft, patient dark of tonight. Sleep well, rest gently, and good night.